So ionic compounds, we've probably already talked about in class a little bit, don't exist as molecules. When you put an ionic compound together and you get positive and negative ions attracting each other electrostatically, they actually form really large crystal lattices where all the positive ions get surrounded by negative ions and all the negative ions get surrounded by positive ions. So the chemical formula of an ionic compound, therefore, doesn't really represent a separate particle or separate particles, little molecules. It's all it is really is the simplest ratio of ions in the crystal. So it's really an empirical formula. And so sometimes the chemical formula of an ionic compound is going to be referred to as a formula unit. The types of questions where this is going to happen are calculation type questions, whereas when we were doing calculations with stoichiometry that had to do with the number of molecules in a certain mass, well, when you try to do a question like that on an ionic compound, it's not really correct to say how many molecules of NaCl are there, how many molecules of sodium chloride are there, in this many grams, because technically it's not composed of little molecules. It's composed just in this giant, massive crystal. So if they want to ask you that same type of question for an ionic compound, they may use the term, how many formula units are there in this much sodium chloride? It's not that common, but I just want to make sure that everyone has seen the term so they know how to deal with it. While we're on the subject of the formula unit, the simplest ratio is 1:1. So the formula unit of NaCl or of sodium chloride is NaCl. So it's the same as its chemical formula. But just to point out, even though the ratio of ions is 1:1, it doesn't mean that we have, again, this molecule of NaCl. So even though this is sort of the smallest unit of it, if you had to describe the structure, you would be better off describing the coordination number of this compound. So for the simplest structure with ionic compounds, every positive ion, in this case a sodium ion, is actually surrounded by 6 ions that are negative. So in this case, 6 chloride ions. If you look at the structure, you can see that for every positive sodium ion, there are, 4 chloride ions visible that are surrounding it, but behind it, there's one there, and if we can imagine, there would actually be a 6th here if the crystal continued. So around every single sodium ion, there are 6 chloride ions, and it works the same way for the negatives. Around every single negative chloride ion, there are going to be 6 positive sodium ions. So even though the ratio is 1:1, it would be a common misconception to think that there's only one ion next to one of the other ions. They're actually surrounded on all sides because of the nature of the crystal lattice for ionic compounds. So sometimes that will get brought up either on multiple choice or on paper 2, and it's just a term they might use. The coordination number of sodium chloride is actually 6. So the ratio of ions is 1:1, and therefore the chemical formula or the formula unit is NaCl, but each ion is actually surrounded by 6 ions of the opposite charge. So let's see how might this show up in a question. So like on paper 1, they might say, how many formula units are there in 5.8 grams of sodium chloride? It really just means like how many NaCl molecules are there, but we can't really use the term molecule because NaCl doesn't exist as molecules. So we could treat it as if it had asked us that question, however. So the first step would be to calculate moles. So 5.8 grams divided by the molar mass of sodium chloride, which is 58, more or less. So we would have 0.1 moles, and 0.1 moles times Avogadro's number. So times 6 times 10 to the 23rd. I'm just going to skip writing it. And it would be 6 times 10 to the 22nd. So there would be 6 times 10 to the 22nd formula units of NaCl. So notice that we did the exact same math if we had been asked how many molecules are there. It's just really a new term that we have to use to be more correct when we talk about ionic compounds. Along the same stoichiometry lines, now that we've talked about ions, you can also be asked questions. Instead of saying how many atoms are there in this given amount of a compound, you could also be asked how many total ions are there in this amount of a certain compound. So in some cases, it doesn't really change anything. Like in this first one, how many total ions are there? in 0.1 moles of sodium chloride. Well, in sodium chloride, there are two ions, just like we could have said there are two atoms in sodium chloride. So you could convert the 0.1 times Avogadro's number and get 6 times 10 to the 22nd is the number of formula units. And then if you wanted the total number of ions, it would just be times 2, because there are 2 ions in every one formula unit, 1 sodium ion and 1 chloride ion. The only place where this gets tricky is with the polyatomic ions, because polyatomic ions look like they are made of many atoms. So in this one, you have to really be able to recognize your polyatomic ions. In this one, it says how many total ions are there in 0.01 moles of calcium nitrate. Well, there's 1 calcium ion, and then there are 2 nitrate ions. So total, there are 3 ions in every 1 formula unit. So again, it's just figuring out that correct ratio. So the first step would be to take the 0.01 moles and multiply it by Avogadro's number, and we would get 6 times 10 to the 21, because 0.01 is the same as 10 to the minus 2. And then we would multiply this times 3, because there are 3 ions per formula unit. So it's all stuff that we've done before. Now we're just applying a couple of new terms, a couple of new strategies, because now we're talking about ionic compounds, and so that changes our vocab a little bit. The other type of calculation that you end up seeing when you're doing ionic compounds is dealing with what we call ionic hydrates. There are a lot of ionic compounds that in their solid phase actually contain a bunch of water molecules bound into their structure. So this is a rendering of an ionic crystal lattice, and you can see all these small water molecules actually attracted to those ions. So the water gets attracted through a type of attraction called an ion-dipole interaction. It's a type of intermolecular force, something we'll talk about in more depth later on in the course. It's a similar attraction to if the ionic compound were dissolving in water, but there's just fewer water molecules around, just some water molecules actually sticking into the structure. When this is the case, the water is actually considered to be part of the structure, and therefore you have to consider it when you calculate something like the molar mass of a hydrate, or if you're asked to figure out the number of a particular atom within a compound. So the water is essentially part of the structure. It's not a separate thing. It's also very typical to do labs, and we'll do an experiment where you heat the hydrated ionic compound, and when you heat an ionic compound, the water that's in there as part of the hydrate will be driven out of the ionic lattice, and that will leave behind the anhydrous or anhydrate form of the ionic compound with no water. So although it may naturally exist as a hydrate, if you heat up the ionic compound, you won't melt it, but you'll drive off the water, and the water will leave as a gas, and you'll be left with the anhydrous form of the compound. And by measuring the changes in mass, so the mass before and after heating, you can figure out the mass of water that was in that compound, and therefore the moles of water that was in that compound. And that's how you can figure out an empirical formula of an ionic hydrate. So for example, this is cobalt 2 chloride 6 hydrate is an example of an ionic hydrate. So cobalt 2 chloride is the ionic compound, and the fact that it's named 6 hydrate means that for every cobalt chloride, there's actually 6 water molecules attached in that crystal lattice. So the mole ratio is that there are 6 moles of water for every 1 mole of cobalt chloride. The way you write an ionic hydrate formula is you have the ionic chemical formula here, CoCl2, then you put a dot. It doesn't mean multiplied by. I know that's how you write it sometimes in math class. It's just the convention. Put a dot there, and then the number of water molecules per that one ionic compound. So the hydrated form of cobalt 2 chloride looks like this with the 6 waters attached, and the anhydrous form is just CoCl2 with no water attached. Okay? And so if we're going to do a molar mass calculation for these two things, for this one, I only have to add up cobalt and 2 chlorides, but for this one, I have to add up cobalt, 2 chlorides, and 6 water molecules to get the molar mass. So if you're watching this video, why don't you take a second, pause the video, and see if you can add up the molar mass of the hydrate and the molar mass of the anhydrate form of cobalt 2 chloride. Okay, if you pause the video, let's see if you got the right answer. So we've got the molar mass of cobalt, we've got chloride times 2, and then we've got 6 times water, which I've just combined as 18.02. So the molar mass of the anhydrous form is 129.83, whereas the hydrated form is 237.95. So you can see in this case, it's a huge, huge difference. The water almost weighs half of the compound. It almost makes the molar mass twice as much. So when you're using hydrates in the lab, it's really essential that you include the water in your molar mass calculations so that you use enough of it because uh, it's a much heavier compound per mole when it has all that water attached. So just something to keep in mind. Also, if we think about a type of question where they say, how many atoms of a given element are there? If we look at the cobalt chloride, for example, they could ask us how many oxygen atoms are in a given number of moles or grams of cobalt 2 chloride, the hydrated kind. Note that it's considered to be part of the structure. So in every one of these, I've got 1 cobalt, I've got 2 chlorides, and then I've got 12 hydrogens, and I've got 6 O atoms. So they could ask us to calculate the number of oxygens, or they could ask us to calculate the number of total atoms. So in this one compound, per formula unit here, we've got 12, and 6 is 18, we've got 20. We actually have 21 total atoms. Okay, so on stoichiometry questions like that, when they ask you for numbers of atoms, you have to include the waters in the calculations for the number of total atoms or atoms of a particular element. Okay. That covers the different types of calculations that you'll see with ionic compounds and ionic hydrates, and we'll do some more practice in class.